I'm going to start recording, and I'm going to raise the desk because I'm more alert when teaching when the desk is raised.
Dr. Cahill, I
Yo,
find it even funnier that the one student in here is also one of the students not signed up for this class.
I'm sorry. Could you say that speaking slowly and more loudly?
Absolutely. Can you hear me now?
Yes.
I find it interesting that the one student who's in this class is also the one student who's not signed up for the class.
The student who's not signed up for the class is the one student who what?
Who's in the class currently? Like I'm not signed up for this Wednesday class.
Okay. All right. Well, yeah. As I said, I think anybody should be able to attend the lectures, frankly. In any event, let me see what was I going to do. Well, first, let me go back to the issue of that homework problem. So I need to go to general relativity, stationary action, and geodesic equation. And I'm going to make it big enough so that you can see. And I've added something that's not in the book, but I think is worthwhile. And if there's ever a third edition, I want it in the third edition. The first equation, though, of course, this part is in the book, and it's the invariant proper time for a particle to move along a path is given by an integral of d tau, and tau is minus and the metric dotted into the differentials, and then you take the square root. Let me see if I can do some of that on the screen here. So we're talking December 8th. So 8 December. So the idea here is that the invariant or minus the invariant is minus GIL dxi dxl. And in the free fall frame, the dx's are 0. And so what you have here is simply minus G00 dt squared and, well, c squared dt squared. And since by the principle of equivalence, this is special relativity holds, and so this is just minus c squared dt squared. So that's the time in the free fall coordinates, and that's the proper time apart from a factor of c. And so what's normally done to evaluate this is to rewrite dxi as dxi d tau times d tau, and dxl as dxl d tau times d tau. And then you've got two d taus that come out of the square root and give you a d tau. And so this is the invariant proper time for particle free falling. And it's extremal and stationary on free fall paths called geodesics, which of course is just the principle of least action, that if this is the action, then setting the variation of the action equal to 0 gives you the classical equations of motion. And now what's you might say, why do people keep quoting this funny form that has this square root in it that's really pretty complicated? And the reason is that this form of the action is, or this action, I should say, is invariant under reparametrization. In other words, if we change from the variable, here you see it's an integral detour, and everything is, this is GIL of x of tau, and this is dxi detour at tau, and so forth. If we change from tau to lambda of tau, then what we have is this, but this is dd lambda is just dd tau d lambda d tau, and dd lambda here is dxl d tau d lambda d tau. And on the other hand, d lambda is d tau d lambda. I'm sorry, that's backwards. What do I want to do here? Now I thought this was really cool, and now I seem to have screwed it up. D lambda what have I done here? Oh, this is backwards. I did this backwards. This, so let me fix this on the fly here. This is, so dd lambda is dd tau, d tau d lambda, and not the reverse. So if I can, so what do I have to do? I have to just take this x and stick it there, and take this x oh God, now I don't remember where I was. Here, let me just put this back. Okay, I think this is better. So let's just see if I've done that right now. One of the problems with tech is that the equations look so good on the screen that you think they're automatically right. So this is dd lambda is then dd tau d lambda, and dxl. Oh God, I inverted the wrong one here. Sorry. All right, well, this was clearly stupid. So this is a little better. And then this last one has to be d dd tau d lambda dd tau d lambda, and we're, let me just, these tech equations are so big that it's oh no, that's the wrong one. No, that is right. All right, let me try to do that. Okay, so that part is right. And now I have to invert this one, and I can't find the damn 1/2 in this thing. You'd think it would be easy as pie. So let me just try this one more time. Oh, I see. I used a funny notation. Okay, and this should be detour d-lambda. All right, I think I'll finally have it right here. All right, I think I finally got it right. Okay, so this is dd lambda twice and a d lambda outside. And in fact, maybe a little too far outside. So then this is d detour d lambda, d detour d lambda. D lambda then is d lambda detour. And now you see what happens is that the detour d lambda comes out and cancels the d lambda detour after you take the square root. And so you're just left with this expression. So that shows that this form of the action is invariant under arbitrary reparametrizations, and as long as they're one-to-one and differentiable in both ways and so forth. And so that's why this funny action is the action that people prefer. On the other hand, and in the text, I may have skipped over this in the lectures, but in the text, if you take the set the variation of that equal to 0, what you get here is this equation. And then you notice that this is the affine connection. And so you get what's the traditional geodesic equation where UL is dxL dTau. And so this is the geodesic equation. Well, it turns out that one can derive this geodesic equation more simply from a simpler action that is not reparametrization invariant, but is vastly simpler. And so what you have here is you just set the variation of GIL, UI, UL, or the variation of this equal to 0. And now using primes to denote differentiation with respect to tau, you can compute that first order variation as this integral over tau, and then you can rewrite that in this form. And then since the variation of xk is arbitrary, you get that this equation, what the square bracket has to equal 0. And you can then rewrite that in this form. Again, you recognize the affine connection, and so you get back to the same equation. So the point is that the utility of this demonstration is that when you change the action, you wind up with the same affine connections. And in fact, it turns out in many cases that it's easier, if you know what the metric is, to just vary the metric and in a particular way, and then you get this complicated expression evaluated more simply. And an example of that is one that I worked out in a little more detail here in the case of the standard cosmologies, where we assume that everything is as symmetrical as possible. So the space is maximally symmetric, and it's just expanding with time. And then there are three maximally symmetric spaces corresponding to k equals -1, 0, and 1. L is some huge number to be determined experimentally. And so you can compute the affine connection this way, but it's simpler to say, to set the variation of this equal to 0 and to say, well, that's going to be the same as this. And in particular, for the variation of the time variable, and here I've got a lambda, and it should have been a t of tau. So let me make that a tau if possible. And then down here, that's also tau. I decided to switch from lambda to tau sort of at the last minute there. And so if you vary it, what happens? Well, it's that what we're varying is t of tau. And so you have a factor of 2, a t prime, and then a t double prime with respect to tau, and then the change in the time. And you see, you have two tau derivatives here, and so when you have that variation of t, well, let's see, maybe I should do this explicitly. So what you want is the variation of dt d tau squared. That's what you're talking about. And the variation is the variation of t. And so this is then 2 dt d tau variation of dt d tau. And so this is 2 dt d tau d tau of the variation of t. And now you integrate by parts and you get -2 d2t d tau squared times variation of t. And so that's how this thing turned into that. That's where this term came from, and the minus sign was absorbed. Over here, t is not occurring very often. It just occurs in a squared. So it's a of t. And so the change in that is 2a dA dt times the change in t. And so this is the expression one gets, and one sets the square bracket equal to 0, and you have this. You identify that with the expression involving the affine connection, and then you get 3 of the affine connection variables. So this is simpler than going through, than computing them directly. Of course, there are computer programs that allow you to compute them directly without doing anything, and some of them are available. I put some of them in that GitHub or JitHub repository that I refer to in the text several times. Let me get this out of the way. Sorry, I had that covered. Okay, so that's the homework stuff, the GR stuff that I was going to double back and do. And now, let me say that I put the first 4 homework problems on the class website, and I'm working on a 5th homework problem. These are tentatively due on the 12th. I can maybe change that date slightly once I get straight when the final exams have to be, final grades have to be turned in. So I think I'll go on with probability and statistics unless you guys, gee, I forgot to start the chat board. That was stupid. of me. So I'm putting chat up here. So please, if you have a suggestion, if you'd rather I did something other than probability and statistics, say so in the chat, on the chat screen, please. And all right, so I'm going to go on with this then. And basically, the basic distribution is the, I want to call it the Bernoulli distribution, which probably is what it should be called. But anyway, it's called the binomial distribution, which is a good name for it anyway. And the binomial distribution is exact. The problem with the binomial distribution is that, first of all, it's discrete. It's the let's see, it's the probability, the B is for binomial, of having n successives in capital N trials if P is the probability of success on each trial. And this is exactly given by this expression here. The problem with it is that it involves these n factorials, which quickly become absolutely huge numbers. And of course, the probability is between 0 and 1, and that's because these things cancel. The n factorials in the numerator and denominator cancel, and the p's and q's are both less than 1 and are raised to a certain power. So these things are actually always, these probabilities, binomial probabilities, are always less than 1 or less than or equal to 1. But computing them can be awkward, to say the least, because these factorials are absolutely huge numbers. Also, you might want to go to a continuous distribution. And Poisson and Gauss made improvements in those directions. Let me first mention or remind you of what I said last time, namely that one way to cope with numerically with big numbers is instead of computing this thing directly, you compute the log of it. And so you write it as the exponential of the log, and then you cancel the logs. And then when you've canceled the logs, you exponentiate. And that's a way of coping. And the way you compute the logs, if you want to do it numerically, is there are various functions in Fortran, C, Python, MATLAB, and I'm sure mathematic, I somehow left out mathematic here. So that's one way, but something that is much more useful, well, that's very useful is what, or in certain limits is more useful, or is very useful, is what Poisson did. And he said, well, let's take the limit in which capital N, the number of trials is huge, and the probability of success on each trial is essentially Zippo, and then compute what this binomial probability is, and then approximate it in this limit. And if you do that, say, using Stirling's formula, which we derived, remember, back in the complex variable section, n factorial is square root of 2 pi n times the nth power of n over e, e being 2.718281828. And so you use Stirling's factorial for the big factorials, and then you take n over big N which is the probability P, let that go to 0. And then the expected number of successes over capital N goes to 0. But you keep the expected number of successes fixed, which is just P times N. And when you do that, this thing with Stirling's formula becomes this. And then after you've done some cancellations, you get that. And now e to the minus x is the limit as n goes to infinity of this. So you can take these two limits and you find that that's e to the average number of successes. And so then you have Poisson's distribution, which is the probability of n successes if the average number of successes is n average, is n average to the n over n factorial e to the minus n average. And you can see that if you sum this from n equals 0 to infinity, the sum of these guys just gives you e to the plus average value of n. And so the thing is normalized to unity. And then the average value of the average success, do I want to say the average success? Yes, the average number, what do I want to say here? The average number of successes is n average, which is what you want. So that's n times the probability summed from 0 to infinity, and then just shifting things a little bit, you wind up with that. The variance turns out to be equal to the average number of successes. And so the mean, the average, and the variance are the same. And so then we can ask, well, how accurate is Poisson's distribution compared to the binomial distribution, which is exact? Let me just raise this a little bit more. And so if you set P equal to 10 to the minus 4, N equal 10 to the 4th, then the average value of average number of successes is 1. And Poisson's approximation to the probability that you get 2 successes, Poisson's is 1 over 2e. And maybe I should show you why that's the case. If we go back to Poisson's, the probability is n to the n over n factorial e to the minus n. And here we're saying that n is equal to 1 and little n equals 2. So this goes to e to the minus 1 over 2, which is 1 over 2e, which is this expression here. The exact binomial probability is then, or Poisson's approximation is 0.18394. The exact one is the binomial value, which is 0.18395. So it's accurate to 1 part in 10 to the 5th. So that's quite accurate. It turns out that coherent states are intimately related to the Poisson distribution. The coherent state of argument alpha, this is an eigenstate of the annihilation operator. A on alpha is alpha alpha. And that alpha is this expression here. And so now you see this is kind of like a Poisson distribution, but if you say, well, what's the probability of finding n quanta in the state alpha? Well, n alpha is e to the minus alpha squared over 2 times alpha to the n over square root of n factorial. And so that squared is absolute value of alpha to the 2n over n factorial e to the minus alpha squared. That's a Poisson distribution where the average number of successes, the average value of n, in other words, is alpha squared. All right, I think we can skip the cancer thing. Now, Gauss took a different limit. What he said is, well, this binomial distribution is exact, but let's take the limit. So let's switch now to Gauss. He said, let's take the limit where the number of successes might go to infinity, and the number of trials is also going to infinity, but P is fixed. And P is then n over big N fixed. So he kept the probability as a finite number and set the two n's to infinity, whereas Poisson sent P and big N to infinity and kept little n fixed. So it's a different limit. And if you do the Stirling massage to the exact binomial expression, then, well, there's a lot of arithmetic here, and I don't think we need to struggle through the whole thing. You eventually get down to an expression for the log of the Poisson, of the binomial distribution times a certain square root, as this expression here. On the other hand, y over pn and y over qn are both tiny numbers, and so you can use the approximation log of 1 plus epsilon is epsilon minus a half epsilon squared. And when you do that, you get that this log is these two things in which most everything cancels, and you just get minus y squared over 2pqn. So then the binomial, the Gauss's approximation of the binomial distribution then is 1 over a square root of 2 pi pq. Remember, q is 1 minus p. Pq capital N e to the minus n minus pn squared over 2pqn. Okay, this is normalized, and the normalization is almost exact for n, for pn greater than 100. One advantage of Gauss's limit is that you can take consider the integer n to be a continuous variable x, and then what you have is the Gaussian distribution, which is e to the minus x minus p capital N over this and that. And now, since this n is somewhat artificial, what one does is compute the average value of x. We can have x go from minus infinity to plus infinity. The average value of x then is Pn, and the variance then is the average value of the square of x minus the average value of x, and that turns out to be PQN. And so these PQNs, this PQN is sigma squared, which is the variance. And so what you have here is twice the variance, so 2 sigma squared here. Sigma, this is sigma squared, so a sigma comes out. So it's 1 over sigma, 1 over square root of 2 pi sigma e to the minus x minus average value of x squared over 2 sigma squared. And this distribution occurs all the time in mathematics and physics, especially in physics and in nature, and it's often called the normal distribution. So in other words, this is what you expect. If you don't have that, something funny is happening and you need to look and see what is it that's going on. Here I see I've got something wrong here. Well, let me just so an example for the accuracy of Gauss's distribution, suppose P is 0.1, N is 10 to the 4th. The probability that N is 10 to the 3rd, Gauss's approximation is this. The exact binomial one, and Gauss's is then 0.013298, and the binomial is 0.013297. So you see these approximations are extraordinarily good in the limit in which they're defined. I think we can skip this biophysics, but if you really want it, I'll go back and do it. Then there's something called the error function, and the way this comes about is if you have a variable x that's randomly distributed according to Gauss's distribution, then the probability that it has a value value mu within a window 2 delta is this. And so it's that integral of the Gaussian. You can transform this integral a little bit until you get this expression here. Well, this is not, we don't have an analytic or a simple analytic expression for this. And so instead we call it the error function, ERF. And ERF of x is just 2 over square root of pi integral 0 to x e to the minus t squared dt. So the probability that x lies within delta of mu is ERF of delta of divided by sigma root 2. That's the x here. And so there are various probabilities that people talk about, and in particular, they use for delta, or for delta, they use the standard deviation, which is the square root of the variance, of course, or 2 sigma or 3 sigma. And when you do that, then you have ERF of 1 over root 2, ERF 2 over 2, ERF 3 over root 2. And these are, so it's 2/3 in one case, and then it's 95%, and then it's almost 100%. And so here is the error function. And so you see the 2/3, 95%, and then essentially 100%. And so in experimental physics, you judge the quality of a result by what the chance is that the result is just a statistical fluctuation. And if you say that it's a 5 sigma, then it's accepted as an actual result. Whereas if it's 3 sigma, well, people say, well, it's very interesting, we need more experiments. And if it's just one sigma, then people just don't pay a great deal of attention.
I have one question.
Okay, you know, if you type it on the chat screen, it'll be easier for me to understand.
It's just, I am just curious to know, like we know that 3 sigma covers almost 99% of our data. And if you take 4 sigma or 5 sigma, that means it covers 100%.
Well, it's not 100%. It's I'd have to compute what that is, but 4 sigma is probably 0.999 something or 9999 something, and 5 sigma is very, very close to 1. But I don't have those things memorized, so I can't really tell you. But what one is saying here is that basically, if your probability of the result being true is almost 100%, then it's accepted. And let's see, I'm not expressing that quite the way I should. In other words, what we're saying here is that if we go back to this, it's that a 3 sigma result means that the probability that the thing is right is 0.9973. And in other words, the probability that a fluctuation or you see, in any experiment, what you're doing is you're typically averaging over many events that have different values. And you then take the average value, and that's your result. The question then is, what is the probability that your average value is wrong? Or how certain are you that your average value is right? And that's basically what's involved here. So let me now go on to something called error analysis here. So the mean value of a smooth function of a random variable x, if it's distributed according to a probability distribution, well, it looks like this. It'll be the average value, x minus the average value times the derivative evaluated the average value, plus a half, x minus the average value squared, second derivative, p of x. And so if you do that, this gives 0, and this gives sigma squared. And so this is our approximation. And that's as long as the higher moments and higher derivatives are fairly small. Then the mean value of f squared, if you compute it like this, is this. And if to find the variance, then you get sigma squared times f prime squared at mu. And if it's a function of several variables, then what you get is you have sigma squared for each variable times the second derivative of each variable, and it's these are all evaluated at the average value of these n random variables. And so if you have something that's a sum, then you can see that the variance of a sum turns out to be this, and the variance of a product, on the other hand, is a more complicated expression, and the variance of the ratio is this. I'm just using the earlier formula, and the variance of a power turns out to be this, and in all this, the standard deviation is the square root of the variance. So then what Gauss's distribution gives us is, of course, the Maxwell-Boltzmann distribution of velocities of molecules in the gas, or of so many other things. So if we start in one dimension, imagine one molecule is being knocked forward and backward by other molecules. Each hit increases its speed by dv, and if there are n hits from behind and capital N minus n from in front, then the speed, if it starts at rest, is then 2n minus capital N times the change in velocity. And the probability of this speed is given by Gauss's approximation to the binomial distribution as, and it's this expression here. And so you get Vx squared over this dv squared. Here, n dv squared is the variance of Vx, and that's the mean value of Vx squared. Kinetic theory says the mean value of Vx squared is kT over m, where m is the mass of the molecule, T the temperature, K Boltzmann's constant. And so what we wind up is the Maxwell-Boltzmann distribution in one dimension. And then if we go to 3 dimensions, we just basically cube this thing, and we get dv, multiplying by dv cubed, we get 4 pi v squared dv e to the minus a half mv squared over kt. So this is just the kinetic energy divided by kt. And then we have a normalization factor, so that the integral over all velocities is unity. And the mean value of a velocity is then 0, because this thing is symmetric. If v goes to minus v. On the other hand, the mean value of the square is 3 kt over m, which is just the statement 1/2 mv squared is 3/2 kt. And that's the old thing of statistical mechanics, that each degree of freedom gets kt over 2 of energy. Now, the commutation and anti-commutation relations of quantum fields, whether Bose or fermion. Bose means that the spin is, intrinsic spin is integral or 0, and Fermi fields it's half odd integral. And in the case of non-interacting bosons, you can put an arbitrary number into the same state, energy state. And so if you compute, you can compute something called the partition function, which is then a sum of these expressions. And so what you get then is let's see, I should, yeah, Z here is then 1 over 1 minus e to the minus beta En minus mu. And that's for bosons or fermions to get this. Well, I went through this a little too fast, I think. Well, on Thursday, I guess I'll pick up here. If you want me instead to cover different material, such as, for example, I could jump to a later section, a later section in this chapter, or I could jump to Monte Carlo methods, artificial intelligence, order chaos fractals, and so forth. So I could jump to some of these things instead. But you'd get a better lecture if you tell me ahead of time than if you just tell me Thursday afternoon at around 6 o'clock that you'd really like to hear something about AI. Well, then, you know, I'll do what I can, but it won't be as good as if I hear from you before class starts that you want to hear something about AI or path integrals or whatever it is that you want to hear about. All right, so I'm going to stop recording now. So I'm going to stop share and